Hello everybody. In our series of lectures on basic electronics, learning by doing, let us move on to the next lecture. Before we do that, let us briefly review the concepts that we learned in the previous lecture. We saw about transistor action, basic action of a transistor, different types of transistors like NPN, PNP, etc. And then we also saw how there is current amplification in the case of a transistor. We also demonstrated using simple circuits. Then we also saw a combination of transistors which is very useful, which is called Darlington pair transistor. So now we move on to look at the transistor in much more detail, and we will try to see the characteristics of a transistor and then look at the various biasing techniques during the course of this lecture. Now, before we make use of any device, we should fully understand its potentialities, how well it can be used in different applications. So, in order to understand the full application potential of a transistor, we must have a clear understanding of its characteristics. Now, I have shown on the screen a circuit which is used for obtaining the output characteristics of a transistor, and this transistor is now used in what is known as common emitter configuration. Now, you can see the emitter is connected to the ground here, and it is common to both the input side from this side to the left or to the output side on this side, and therefore this is called common emitter configuration. So, the transistor in the common emitter configuration, I am looking at, there is a power supply here which is called VBB for the base supply, and this is a current ammeter for measurement of IB, the base current, and there is also a collector current meter which is called IC here. It is in milliamperes. The base current meter is in microamperes, and then you have also got a voltmeter which is connected between the collector and the ground or the common terminal, which will measure the VCE, the voltage between the collector and the emitter junction. Because the emitter is grounded, this voltmeter will read the voltage between the collector and the emitter. Now, this is called common emitter configuration, and if I find out the relationship between IB, IC and VCE, this characteristics is called output characteristics of a common emitter configuration transistor. You can imagine that we can also have a voltmeter connected here between the base and the emitter, which will measure VBE, and if I now plot the graph between the different values of base current and the VBE, the voltage between the base and emitter, for different applied values of VCC, then we will get another set of characteristics which is called input characteristics of the transistor. So, what we are now doing is basically on the output side at the collector and the emitter part of the circuit a transistor, and therefore this is called output characteristics. This is just one example of several characteristics that you can think of in the case of transistor. For example, you can also have common base characteristics. Again, you will have input characteristics and the output characteristics, but the transistor will have the base as a common terminal between the left and the right side, the input and the output side. Similarly, you can have common collector characteristics and things like that. Each one of them will give us some information about how it can be used in different applications in that particular configuration. But because common emitter configuration is the most popular and very useful configuration for several amplifier type of applications, we are concentrating on common emitter configuration. So, the common emitter configuration you have already seen in the circuit. Now, what we do here is you set by first switching on the VBB voltage source, you allow a small current of maybe let us say 10 microamperes or so set in the IB ammeter. Because this circuit is complete between the base and the emitter, you can set a current of 10 microampere using the VBB power supply by varying this, and it will be very small voltage that you have to apply in the order of hundreds of millivolts. You would find you will be able to measure have about 10 microamperes current set here. You keep this current constant IB value. Now what we do, you start varying the VCC supply from 0. The arrow here indicates that it is a variable voltage source. So you vary the voltage by using a knob, you vary the voltage from starting from 0 in some specific steps, for example 0.5 volts or so, and then find out what is the collector current for each of these voltages, and also record the VCE. You know, because the ammeter is a low resistance device which is in series with the transistor, the voltage VCE will almost be equal to the voltage VCC that you apply. So if you know what the voltage you are applying, then you do not have to measure this VCE, but in principle this shows that we are now here monitoring the voltage between the collector and emitter. So for just by keeping IB constant, you vary the VCC voltage from 0 to some fixed value, for example 10 volts or 15 volts in steps of 0.5 volts, and record for every step what is a collector current IC, and plot a graph between VCE and IC. That is what I want to show you in the next graph. Now you can see I am plotting on the x axis VCE, the voltage between the collector and the emitter, and on the y axis IC, the current at the collector. For different IB value, this is one value of IB I have maintained, and you find as we increase the VCE, initially for a very small voltage variation the current increases linearly, and after that, for example in this case when the current IC reaches 1 milliampere current, you find irrespective of the voltage you apply on the VCE, the current remains constant. And if we go beyond some limit, very large voltage VCC, then you would find it might even break down, and then there will be a very large current flowing without any change in the voltage VCE. So this is one single characteristic for one single IB value. When you vary VCE or VCC continuously, you get one such graph. Now what we do is we go back and set a different value of IB, IB2 maybe 20 microamperes, and again repeat by varying this from 0 to large value 20 volts or 15 volts, and record the corresponding IC and plot them in the graph. And likewise you keep on doing for different values of IB, and what then you will get will be a figure as shown now. You find here, this was the first graph I showed you, IB is equal to 10 microampere. Now we do with 20 microampere one more time, 30 microampere, etc. You would find this will be the family of characteristics that you will obtain for this case for different values of IB, the corresponding values of VCE and IC. This should be VCE, not VCB. Okay. Then we should also remember now that every transistor comes out with a very specific power rating. That means the maximum power that it can dissipate, which is given by the product of VCE into IC in this case. So when it exceeds the maximum power allowed for a given device, then we should not go beyond that point. So VCE IC is equal to constant. Well, if it is for example 1 volt, if IC is very small, the VCE can be very large. As we change the IC, you would find the VCE, maximum value of VCE, keeps decreasing. So it comes something like a rectangular hyperbola, and therefore I should never make my transistor work anywhere in this region which is beyond this curve, which is corresponding to the maximum power dissipation curve. So this is about the region in which we would like to operate, and even here there are three different regions that we should identify. One is this region very close to the x axis, which is called the cutoff region. This is the cutoff region below which if I have an IB, I will never have any IC at all. That is the cutoff region. So I must have this is the minimum IB I should have to make my current IC have some specific value. Now then there is also another region which is parallel to the y axis or the collector current axis, and this region is called saturation region. The saturation region is a region to which I reach very small variations in the emitter voltage, collector emitter voltage VCE. I reach this point. Afterwards there is no variation, it has already reached the saturation. All the electrons or the holes, as the case may be, have been collected by the collector, and therefore even if I increase the voltage, there is no change in the collector current almost. You can see that true when there are very smaller values of base current, it is almost flat, but as I increase the base current, you find the slope slightly changes from being purely horizontal. Okay, this also can be understood. Now therefore you find there is a saturation region and there is a cutoff region, and the rest of the region in between this maximum dissipation curve and the saturation and cutoff region, what you have is called the active region, and this is of very great importance to us, because all our amplifiers, whenever I use a transistor as an amplifier, I will always try to use the amplifier in this region. So I already mentioned to you that in the characteristics is a very important step forward in designing different circuits. So we should understand the characteristics of a transistor. This is the output characteristics of a common emitter transistor, and we have seen the active region in this region. And now what we have to do is, any given circuit can be positioned on the characteristics at a given point. So this positioning of a transistor at a very given point in the active region is called biasing, right. So a transistor has to be biased to make it come to a very specific point, which is called the operating point or the quiescent point of the amplifier, and that is what we are going to now look at. Now before I do that, I will quickly show you a simple demonstration or simulation of the characteristics of a transistor. On the screen you can see you have a breadboard and you have a transistor here, the emitter, base, collector are shown here, and you on this side there is a power supply which has got two outputs. One is for the VBB or the base supply, the other one is the VCC supply that we already saw. Even here you can see the same circuit is shown. There is one IC meter and there is one IB meter, current meter, and the two power supplies. That is all you require for doing the characteristics of the transistor. Now there are two multimeters on to your right. The first one is measuring the base current. You can, if you follow the two curves, you can see it is connected here with the base supply. It comes in series with the base and the emitter junction of the transistor. Similarly on the collector side, I have one more ammeter, the multimeter used as an ammeter, milliammeter, and that is for measuring the IC, the collector current. So I have the two power supplies and I have two current meters, ammeters and voltmeters, all made out of multimeters, digital multimeters chosen in the current range. Now all that I have to do is, let me switch on the power supply, let me switch on the voltmeter, current meters, two current meters. Now I am ready. I will now vary the VBB, the base voltage, in steps of 100 millivolts, and as I vary this, you can see the corresponding current, base current, keeps increasing. Now it is 4 microamperes. For 400 millivolt I increase to 500 millivolt, it goes to 5 microampere. So if I keep on doing that for 1000 millivolt or 1 volt, you find it is about 10 microamperes in a typical case. This is reasonably, it is a large voltage, even less than that you would get. Okay, now what I am going to do is, I am going to vary the VCC supply, which is at the bottom, continuously in steps of, let us say, 0.5, and see what happens to the collector current. I am going to keep the IB constant, the base current constant, and I am going to vary the VCC, and for every value of VCC I apply, I will measure what is the collector current. Now let me increase, now it is 0.5 and it is now 0.1 milliampere IC. Now it is 1 volt VCE and it is 0.5. 1.5 it is about 1 milliampere. 2 volts, now it is 1.5 milliampere. 2.5 it is about 2 milliampere. 3 it remains at 2 milliamperes. 3.5 again 2 milliampere. So you can see beyond 2.5, even if I go up to let us say 6 or 7 or 8 volts, you would find the milliammeter shows the same value of IC, which is 2 milliamperes. That is what we saw in the characteristics. Now let me quickly come back to 0 for the VCC and increase my base current from 10 microamperes to the next value, which is for example for 2 volts 20 microamperes. Now let me keep increasing the VCC, and as I increase, please observe what happens to the IC. You would find IC keeps on increasing. The moment I come to 2.5, it is now 4 milliamperes. Beyond that, you find it continues to be in 4 milli. It has already reached the saturation value and it is now 4 milliamperes for all the different voltages that I apply at the VCE voltage. So I can keep doing it for different values of IB, and I have shown here the characteristics. You can immediately see when the voltage IB is 10 microamperes, the IC is constant at 2 milliamperes. When the IB is 20 microamperes, it is constant at 4 milliamperes, etc. And this is exactly the characteristics that we saw in the previous case when I discussed about the output characteristics of a transistor. So now we have done an experiment, simulated experiment, to observe the output characteristics of a transistor. Yeah, same experiment can be performed in the lab and you would get almost similar characteristics. Now the transistors are useful in building amplifiers. One of the main applications of transistor, which is an active device, is that it is capable of magnifying any input signal into much larger value at the output. Therefore, any amplifier in general should have 2 terminals at the input. For the input, you have to connect any microphone or whatever signal that you want to amplify between these 2 inputs, and there should be again an output terminal with which I will either load a loudspeaker if I want a simple audio amplifier, or I can use some motor or device which I want to drive after magnification or after amplification. So every amplifier is called a 4-port network. You have got 4 ports, 2 for the input and 2 for the output, 4-port network. This can be something like a black box. Black box means we don't know anything what it is inside, so just we assume it to be a black box. So an amplifier has got 4 terminals, 2 for the input, 2 for the output you require. But if you look at the transistor, any transistor for that matter, it is a 3-terminal device. It has got a base, emitter and a collector. So how do I make an amplifier which requires 4 pores with only 3-terminal transistor? Therefore you can imagine that I must have one of the terminals as common to both input and output, and that is how I already mentioned to you that the transistor can be used in different configurations, where the emitter can be common for the input and the output in one case, or the base can be common for the input output, or the collector can be common for the input output, etc. So now let us look at the various possibilities. For example, the first figure is a common emitter configuration. You find the emitter is a common terminal. Both 2 and 4 belong to the emitter, and 1 and 2 is the input, 3 and 4 is the output, as in any amplifier. Similarly, you have a common base configuration where the base becomes common to the input and the output, and common collector where the collector becomes your common terminal between the input and output. Okay, with this understanding, now we will concentrate more on the common emitter configuration, as I already mentioned to you, that provides us with large amplification, voltage amplification. Therefore, how do I make use of an amplifier, a transistor as an amplifier? The first and foremost thing that you have to do is that you must position your amplifier somewhere with an operating point, somewhere in the active region of the characteristics of the transistor, whatever transistor that you choose. So, the moment you get a transistor, you should first plot its output characteristics, then you are very sure of how it will perform in a given situation. Then you should try to position the operating point of your transistor on the characteristics at a given operating point carefully chosen. One has to choose carefully that operating point. How do we choose? Now, that is what is known as the biasing of the transistor. This technique is called biasing. Putting the amplifier or the transistor at a given operating point with reference to its output characteristics is what we call in general as transistor biasing. Now, if you look at the figure, you can see there is output characteristics drawn here, very familiar to you by now, and you have to put it somewhere here. This is the active region, you have to put your transistor somewhere here. What it means is every point here will be characterized by a corresponding IC and a corresponding VCE and a corresponding IB. So, to put a transistor on a given point or an operating point on the characteristics is equivalent to saying you must provide your constant value of VCE, constant value of IC and a constant value of IB to start with. That is what is called transistor biasing. And obviously, you can see this can be done in more than one ways. Now, you can see on the left side there is a circuit which is again in common emitter configuration, and you are connected your RB, the base resistance, along with a base voltage source VBB. Similarly, there is one collector resistance which is here 3 kilo ohm, and that is connected to another collector emitter voltage which is 15 volts, the VCC supply as it is called. Now, can I use this circuit to bias the transistor? The answer is indeed yes, you can do that, because you have the voltage and the RB. With this you can forward bias this base emitter junction and you can maintain your constant current. If necessary, you can vary these or choose a proper value of RB and VBB and you can maintain a constant current. And this again with the 15 volts here and the 3K, you would find because there is forward biasing, there will be a current in the collector and the emitter, and therefore that will correspond to your voltage being developed across the collector and the emitter regions of the transistor. So, it is in principle possible to bias in the simplest way by using two power supplies and two resistors. Now, I have written some equations here which will become very simple now to understand, I hope. Now, what is VCE? What is VCE? VCE is the voltage V between the C and E, the collector and the emitter region. So, this voltage is called VCE. Now, you can see that VCE is not the same as VCC, because there will be a finite current flowing, and that finite current will produce a voltage drop across this 3 kilo ohm resistor RC, and therefore the voltage here will be less than 15 volts. Therefore, VCE is VCC, that what I have here, minus the voltage across the 3 kilo ohm, which is minus IC, the collector current, into RC, which is the 3 kilo ohm resistor that I have shown here. This is the RC. So, in general, VCE in this type of a circuit is equal to VCC minus ICRC, which is a very simple equation corresponding to Kirchhoff's voltage law. The total voltage, if you go along the loop, should be algebraic sum should be 0. Therefore, the 15 volts should be dropped among these two devices. One is the resistor, the other is the transistor, and that is what this equation is about. So, now you can see there are two things that I can vary. For example, I can vary, the IC can change, VCE can change, and therefore this becomes a equation which corresponds to a straight line, and therefore this straight line equation is called load line, because that RC is the load which is connected in series with the transistor. So, these characteristics to a particular load or the resistor that I connect here. Therefore, this is called the load line, DC load line, because it is now under DC condition. I have not applied any alternating voltage yet. So, this is the DC load line, that is what I showed here, but how for a given value of RC and VCC I will get a very specific load line. How do I do that? Now, let us assume when IC becomes 0, when IC becomes, that means there is no current through the collector. When will that happen? That will happen when there is no base current, or the base current is too small to switch on the transistor, to forward bias the transistor. Then there will be only IC, the IC will become 0. When the IC is 0, then the voltage IC RC is also 0, because anything multiplied by 0 is 0, and therefore there is no drop across this 3 kilo ohm or the RC resistor, and therefore entire VCC will be appearing across the transistor VCC. That is what this equation shows. When IC is 0, this term becomes 0, and then VCE is nothing but VCC. That is what I have written here. So, I know this point. I go, IC is 0 is corresponding to the x axis, and at that place VCC is 15 volts. So, VCE is 15 volts at IC is equal to 0. Therefore, I have put a dot at 15 volts on the VCE graph, VCE line. Similarly, when the voltage across the capacitor, the transistor VCE becomes 0, then IC will be maximum. IC will be VCE by RC from the same equation. When VCE is 0, VCC is equal to IC RC, or IC is equal to VCC by RC. So, this is VC, this should be VCC. IC is equal to VCC by RC, and therefore this point on the VCE is equal to 0 line, which is the y axis, is corresponding to VCC by RC. So, for a given transistor biasing circuit, the transistor circuit, I know VCC, I know RC. The moment I know these two values, that I choose these two values, I can immediately draw a load line, because for drawing a straight line minimum you require 2 points. One point is corresponding to IC is equal to 0, which is the VCC point on the x axis, and the other point is corresponding to VCE equal to 0, which is nothing but VCC divided by RC, which is on the y axis. So, the moment I know these points, I will take a scale and draw a line between these two, and this becomes my load line. That means all my circuits having the same VCC and the same RC with the transistor will always be somewhere along this line. I do not have to concentrate on any other point away from this line. All the time my transistor will be only along this point. Where it is might depend upon how much base current I give. If I do not give any base current, there is no collector current, so I will be at this point VCC. If I give large current, then you would find that I will be at this point. In general, for different base currents, I will find myself along this line, somewhere along this line, and therefore this gives me the different operating points that I can choose for my transistor amplifier with this specific value of VCC and RC. If I change my RC, correspondingly the straight line also will change, as you can see. Again, if I change my VCC, again this will change. If I change my both VCC and RC, the whole thing will change. Of course, if I change the transistor, the whole characteristics will have to be drawn again. It will be a slightly different characteristics that I will have. So, this is about DC load line. Once you know the DC load line, then you can take up a quiescent point on the transistor. Now, I have given a simple example. So, VCE, if I want to measure, that will be supply voltage minus voltage drop across RC, that is what is shown in this figure also, and therefore VCE is equal to VCC, again this has to be VCC minus IC RC, and if the base bias voltage VB is such that the transistor is not conducting, then IC will become 0 and VCE will become equal to 20, similar to what I already mentioned to you. And similarly, when IC is equal to 0, VC is 20. Also, when IC is maximum corresponding to 2 milliamperes, 2 milliamperes into 10 kilo ohm, in this case it's 20 volts, milliampere and K will go, 2 into 10 will become 20, 20 minus 20 is 0, that corresponds to the point on the y axis. So that is 2 milliampere point when Vc is equal to 0. That is how the load line is obtained. Now for example in this given circuit, if I choose a value of IC 0.5 milliampere, so you can see the 0.5 milliampere passing through 10K will give me 0.5 into 10, which is 5 volts. So milliampere and K again will go. So I will have 10 0.5 into 10 gives me 5 volts. 5 volts I will have to subtract from my 20 volts supply, and therefore VCE will be only 15 volts. I hope you can see that. This is 20 volts, this is 5 volts, and therefore 20 minus 5 is 15 volts. That is what I have here. It will have 15 volts. Similarly, if I have IC of 1 milliampere, 1 milliampere is 10K is 10 volts, therefore the balance 10 volts will be across VCE. When it is 1.5 volts, it will be 5 volts, etc. So there are different points that I can plot on my load line. This corresponds to, for example, this is corresponding to 15 volts when I have about 0.5 milliamperes into 10K. This corresponds to 10 volts when I have 1 milliampere IC. This corresponds to 5 volts, that corresponds to 1.5 milliampere on the correct IC. So all these points are some chosen points, but you can choose any of these points or anything in between, but you will never find anywhere away from this line as long as you have the same VCC supply and same RC. That is what we mean by the load line. Okay, what is the use of the load line? As I already told you, I can choose a Q point very quickly. From the big graph, I have now confined myself to one single straight line, and I have to position myself somewhere along the straight line. Where do I position for best performance of the amplifier is the next question that I should ask myself. Before we do that, now let me see what will happen if I change the load RC value to 9K. This is the same circuit similar to the previous one, except that I have now, instead of the 10K resistor that I have here, I replaced it by a 9K resistor. Then what will happen? You would find VCC is still 20 volts, and therefore VCE when IC equal to 0 is also 20 volts. So the one point in the graph is the same, 20 volts on the x axis. But when you come to the maximum current point or the point along the y axis, you would find IC is VCC by RC. VCC is again 20 volts, but RC now changed to 9K, and therefore it has become a new current 2.2 milliamperes, and therefore you will be in a new point along the graph, which is here corresponding to 2.2 milliamperes. So the moment I have this point and this point, I can join them by a line here I have shown by a dotted line, and this corresponds to a new load line because the load is changed now. You have changed the load from 10K to 9K, therefore you are obtaining a new line, right. So that load line will change whenever I change the load, which is the RC, or when I change the VCC. When I change the VCC also, it will go somewhere along this line, so it will be a new point, and when I change both, that also can lead to this type of a new load line. That is what I want to show you. Okay, now let us move on to the next point. Now let us assume that I put my amplifier somewhere in the middle here. If I put it in here, that means I choose my IB to be 20 microamperes, I choose my IC to be somewhere here close to 1 milliamperes, and my VCE is around 9.5 volts. If I set all these voltages and currents by biasing my transistor in different ways, I will discuss in detail a little later, then I will be operating at this point. This is the Q point of my amplifier or whatever. Now if I apply a variable voltage or the AC signal to the base of the transistor, then what is going to happen? Over this voltage which is required at the base to provide a current of 1 milliamperes, I am superposing another alternating voltage. So this effect of this alternating voltage is to vary the whatever voltage I applied at the base slightly by the amplitude of the AC signal. So when that happens, you would find my base current can vary according to this change. So when the base voltage together with the AC applied voltage increases, I will move along this line and go to maybe a new position corresponding to IB is equal to 30 microamperes. And when I go down, I will come below that operating point Q, chosen point, to a value, for example, 10 microampere below. That means my current 20 microamperes is going to vary plus or minus 10 microamperes due to the AC signal that I applied, which is understandable. When the base voltage increases, base current also should increase. When the base voltage decreases, base current decreases. So you find my Q operating point will start shifting when I apply an AC between IB is equal to 10 microamperes to IB is equal to 30 microamperes, even though at the beginning when there no AC voltage applied, I was at IB is equal to 20 microamperes. So you find when this happens, the corresponding to these 2 points, the collector current also changes. As you can see, this is around 1.4 or 1.5 milliamperes, and this point corresponds to about 0.5 milliamperes. So you find when this base current changes by a very small 10 microampere range, the collector current changes from the operating point 1 milliampere to nearly 1.65 milliamperes to 0.5 milliampere, nearly about 1 milliampere plus or minus 0.5 milliamperes. And therefore that when passed through a RC of 10K can give me 0.5 into 10, 5 volts plus or minus 5 volts. So that is what is shown here. I can get a swing of about 10 volts about this quiescent point when I have this point. Right. Now if instead of this point I have chosen my operating point at the beginning to be this point, then for the same variation of the signal at the input, you would find I will be moving from here to here, that is IB is equal to 0 to IB is equal to 20 microampere, and that way you would find I will get into trouble, because if it goes beyond this, is already in the cutoff region. I should never come into the cutoff region when I am designing amplifier. Therefore you would find it is always good to choose the point which is at the center of the load line, so that it allows for equal excursions on both sides of the quiescent point. If I go towards this end or towards that end, you would find one side the range of available distances are very limited, and therefore you will get into what is known as distortion of your signal. If I apply a sine wave, I will not get a sine wave, true sine wave at the output, it will be a distorted sine wave, because at beyond some point I enter into a saturation region or the cutoff region, as the case may be. And therefore the general rule is you try to choose a quiescent point which is at the center of the load line. Thereby you would find you will have equal excursion. But this also brings in the concept that there is only a limited amplitude of the signal that I can apply without distortion to get it at the output. So if my input signal is too large, that means it goes from minus 20 microamperes less than by more than 20 microamperes on either side, you would find I will enter into the cutoff region and the saturation region, and therefore it will lead to some distortion at the output. And therefore in general by drawing the load line and choosing the Q point, I become very familiar what is the maximum amplitude that I can apply at the input to obtain undistorted wave at the output. So this also is one of the very important considerations in looking at the load line. Now let us move on to the different biasing circuits. So one of them is a very simple biasing circuit that I already discussed to you, and that is you use a voltage supply for the base and you use a base resistor. But instead of using a separate power supply for base, you already have a VCC supply, and therefore I can take the base resistor and connect it to the VCC there. So now the same VCC is providing the IB as well as the IC that I require. So this is a very simple scheme of biasing the base by providing a constant current for the base. For considering this type of biasing circuit, all the knowledge that you have to have is just simple Ohm's law and some basic circuit ideas like the KVL and the KCL. Now can we calculate what will be the base current for the given case here with VCC 15 volts and the RB, the base resistance, is 820 kilo ohm. What is the base current? Now you can see, as far as this circuit is concerned, there is a voltage drop across the base resistor and there is a voltage drop across the base emitter junction of the transistor, and then you are back at the ground, and therefore the voltage across this plus the voltage across the VBE should together add up to 15 volts according to KVL, Kirchhoff's voltage law. Therefore my IB is nothing but the voltage available across the resistor, which is on this side VCC, on this side VBE. So VCC minus VBE divided by RB, the value voltage, divided by resistor is current according to Ohm's law. So this is simple assertion of Ohm's law, that VBE usually depends on the nature of the transistor, whether it is silicon transistor or germanium transistor. Most of the silicon transistor, when it is conducting reasonably well, it should be around 0.7 volts, 0.65 to 7, usually it is taken as 0.7. So VCC minus 0.7 by RB will be the base current. In this case VCC is 15 volts minus 0.7 is about 14.3 volts divided by RB, which is 820 kilo ohm. So if you work out 14.3 divided by 820, this is kilo ohm, that is voltage. So this kilo, you would find the whole thing will come in microamperes. So IB will be approximately few microamperes. That is what this circuit is used to set. Okay. Now what about the VCE? Can I get the value of the VCE? Yes, you can also get the value of VCE and IC from this circuit. Now you have got, this is from the load line, we have already discussed that. 15 volts, you have 2 kilo ohms, there is a voltage drop across 2 kilo ohms, and the balance is available at VCE. So if you measure VCE, you can calculate IC, or if you know what the IC is, you can calculate VCE. But IC and IB are related by another factor, you know that is called beta, the current gain, DC current gain of the transistor in a common emitter configuration, and the current gain is nothing but almost equal to IC divided by IB, that is the current gain. And therefore if I know the current gain of the transistor, which also can be obtained from the characteristic curve, then I can find, if I know IB, I can calculate IC. IC is nothing but beta times IB. So I know IC, once I know IC into 2 kilo ohm gives me the voltage drop across RC. So VCC minus RC gives me VCE. So I can immediately find out what is my VCE, what is my IC, what is my IB. So that means I know where exactly on the load line I have my Q point. So the biasing therefore now here means choosing proper value of RC, IC, IB, and thereby getting a given value of IB, IC and VCE. That is what we mean by biasing. So this is a very simple scheme of base bias. Now I have worked out some values here, let me see. So we want to design a fixed current bias, the circuit that is shown there, using a silicon transistor. That means VB is about 0.7, having a beta DC value of around 270, typical value, and VCC is 15 volts, and the DC bias conditions, what we want is we want a 6 volts VCE and IC should be around 5 milliamperes. You can choose an approximate value like that. So now RC is VCC minus VCE by IC, 15 volts, you want 6 volts, therefore 15 minus 6 gives me the voltage across RC, that divided by the given current 5 milliampere gives me what is the value of RC. I find 15 minus 6 is 9, 9 by 5 is around 1.8 kilo ohms. So we can choose 2 kilo ohm, which is the nearest value available, preferred value. Now how do I get the value of RB? To get RB, I already mentioned to you, beta DC is nothing but IC by IB, or IB is IC by beta DC approximately, and therefore IC is 5 milliamperes, beta DC is given as 270 milliamperes. So if you calculate, it comes to around 18.5 microamperes. That will be the value of IB. So once I know IB, I can calculate what will be my RB. So I am interested in knowing RB. IB is nothing but VCC minus VBE divided by RB, we have already seen. So VCC minus VBE, which for silicon transistor is about 0.7, divided by IB now, which is we obtained as 18.5. When I do that, I get approximately 820 kilo ohm. So when I put 800 kilo ohms here and 2 kilo ohms here and apply 15 volts power supply in this circuit, I am very sure I will be very close to VC is equal to 6 volts and IC is equal to 5 milliampere, and as long as my gain, DC gain at the particular point is around 270, which is reasonably close, typical value. So what the results of the calculation, VC is 6 volts and 5 milliamp, that is given to us, and we have calculated that the current is around 18.5 base current and the VB is 0.7 for silicon. The RB value we obtained is 820, 15. When we do this experiment later on, you would find this corresponds to the corresponding value that I have given. Maybe I will quickly go on to the working table and show you the same circuit, and I will measure the different voltages. You would find the voltages will come almost very close to the value that we have obtained in this case here. So you can see here the same circuit is shown. It is a fixed bias base bias circuit. I have chosen from the same VCC supply or resistor RB. I connected to the base of the transistor, and the RC is 2 kilo ohms. You can see this is the 2 kilo ohm resistor from the color code, you can see, and this is the 820 ohms 820K resistor that we just now obtained for the circuit, and the emitter is grounded. This is the transistor, and I have a current meter connected at the collector. Between the 2 kilo ohm and the collector, I have connected the current meter, and this is actually the voltage point, the collector point I have connected here to this multimeter, which I will switch on. So the multimeter is now switched on, and the other end of the multimeter is connected to the ground. The voltage supply is taken from here. Let me switch on the power supply. Now you can see the power supply reads around 15 volts, 14.9 volts. Now I connect this power supply to this circuit. The moment I connect, I have 820 kilo ohms at the base, and I have 2 kilo ohm as the RC, and the transistor is there. I am monitoring the collector voltage, and the collector voltage is around 6.72. We wanted to have around 6 volts, it is around 6.7, and you can see the current is about 5 milliamperes. So the same thing which we designed there, we have implemented there. You find the voltage and the current are very close. There are some changes. For example, instead of 6 volts, you are getting about 6.6 or so, and that is because these resistors have got some tolerances. As we all know, it may not be exactly 820 kilo ohms, and this 2 kilo ohm may not be exactly 2 kilo ohm, etc. So due to small variations in these, you are getting slightly different value of voltage or current, but this is quite possible in any given amplifier circuit, and these small variations in general will not make any great variations in terms of the performance of the amplifier. So now we saw one biasing circuit which involved a base resistor which is connected between the VCC and the base of the transistor. But there is another way of constructing a biasing circuit also, and that is, I will show you on the graph, on the picture. Now you can see on the picture, instead of connecting this base resistor to the VCC supply here, I have connected to the junction between the collector and the RC. That means I am getting the voltage from the collector. The collector voltage is used for driving a current through the base. This is called collector base bias. This is a collector base bias. Collector is used to bias the base, and now you can see it has got certain advantages over the previous circuit. Again, to understand the circuit, all that you need to have is simple ideas of Ohm's law. So now what is going to happen, you find you have the current flowing through the RC. The current flowing through the RC previously was only IC. Now this is actually dividing here, IC is a current actually flowing through the collector, and there is also another current which is flowing through that is called IB. So what flows through the RC will be now IB plus IC, because the total current IB plus IC divides into IB and IC here, and what you get is an IC there, and this comes out as IB. And therefore we must remember in our equation, instead of using IC, I should use IC plus RB for the RC, and therefore VCE now will be VCC minus RC into IB plus IC. That is what will give me VCC. And to get IC, what I have to do? VC minus VBE divided by RB. VBE is 0.7 for silicon transistor. VC is the voltage at the collector, which is nothing but VCE. VCE minus 0.7 divided by RB will give me IB. So it is possible to design, for example, I have given an example problem here, design a collector to base bias circuit for the conditions specified in the example. What is that? VC same as the previous one. VCC is 15 volts, and now VCE is chosen as 7.5 volts. In the previous circuit we had only 6 volts. Now we can have 7.5 volts. Beta is 270. The current we want around 4 milliamperes. So IB is IC divided by the gain, current gain, 4 milliamps divided by 270. This is around 15 microamperes. So once I know IB, now I can find out RB, which is VCC minus VCE minus VBE by IB. It is not VCC. In the previous case it was VCC. Now it is VCE minus VBE. 7.5 minus 0.7 by 15. That comes out to be around 453 kilo ohm. So we can use nearest value 470 kilo ohm as a standard value. So what is RC? RC is VCC minus VCE divided by total current IB plus IC that we already discussed. 15 minus 7.5 divided by 15 microampere plus 4 milliampere, which is almost equal to 4 milliampere, and the value is again 1.8 K or 2 kilo ohms. So when I do this, you would find again the corresponding voltages will be obtained. I will quickly go and show you, modify the circuit and show you the corresponding values. Now you see the circuit here, it is now the collector to base bias. The collector terminal is used to connect the base resistance, and other than that everything is the same. So you see this is the resistor which is connected from the base to the collector, that provides the base current bias. Now again we have 15 volts here, you can see about 14 milliampere, and I have the current meter here which measures IC, and this is the voltmeter which measures the voltage across the collector. Now I connect the power supply. The moment I connect the power supply, I get a current here. If you carefully observe, it is slightly less than 5 milliamperes, it's about 4 milliamperes, and the voltage that is measured is 7.76. we wanted 7.5 volts, that is coming to be 7.7 volts. The difference I already mentioned to you is due to some small variations due to the tolerances of the resistor. So the same transistor, I have the 470 kilo ohm connected here and the 2 kilo ohm as the RC, and correspondingly you get the same value which almost you wanted to obtain by using the discussion that we already had. So you have the collector current 4 milliamperes, the VCE is around 7.5 volts, the IB 15 microamps, VBE is 0.7 for silicon, VCC is 15 volts, the RB we calculated to be 470 kilo ohm, very close to 470, and the beta DC is 270 I assume for this transistor. RC, the load resistor, is 2 kilo ohm. So we have now got two different types of biasing circuit. One is the fixed base bias circuit, where I used the VCC itself as a biasing voltage, and I put an RB in series along with the base to provide a constant bias for the transistor. The second circuit is, instead of using VCC, I used the voltage at the collector VC to provide the bias, and so a resistor connecting the collector to the base was responsible for providing the base current. And with these two biasing circuit, we will have to have one more better, more useful or more common biasing circuit, which is voltage divider bias circuit with the emitter bias, and that I will discuss in the next lecture. You would find that has got slightly better performance in terms of stability. So, I use a new term stability, therefore, I have to explain to you what I mean by stability. So, we will discuss in the next lecture about the voltage divider bias and the emitter bias, and then I will also discuss what is stability and how the three different circuits that I discussed, biasing circuits, will perform in terms of the stability. All those things we will see, and then we will move on to look at an amplifier making use of the transistor. So, we will look at the so far what we have done today is to look at the transistor load line, transistor output characteristics, and how the load line is a very important part of the design of any amplifier, and then we will discuss two different biasing circuits, the base bias and the collector to base bias. So, thank you very much.